Alright, so in today's video, we're going to talk about the squeeze theorem. And right here, I have a diagram of what the squeeze theorem actually tells us. But what I'm going to do first, I'm going to explain the actual language of the squeeze theorem and the mathematics behind it. And then from there, I'm going to go to this diagram to explain how the diagram represents the squeeze theorem. And then from there, we'll do three applied examples of using the squeeze theorem. So what the squeeze theorem says is that if you have some function f of x, which is bounded by two other functions, which we can call on the lower end h of x and on the upper end g of x, and if the limit as x approaches some number a of h of x is equal to the limit as x approaches a of g of x, which is equal to some number L, we'll call, so some number L, then we can deduce that the limit as x goes to a of f of x is also going to be equal to L. So let me go ahead and go to this diagram to explain what that all means. So basically what this is saying is that if we have a function f of x, which is in blue right here, and it's bounded by an upper and lower function, so in this case that would be g of x and h of x, so that is this condition here, and the limit as x approaches a of the upper and lower functions are both equal and equal some number L, so in this case the limit as x goes to infinity of both h of x and g of x is equal to 0, then we can say that the limit as x approaches infinity of f of x is also equal to 0. So let's go ahead and do some applied examples of the squeeze theorem. So our first example is find the limit as x goes to 0 of x cubed cosine 2 over x using the squeeze theorem. So the first thing I'm going to do whenever I have a squeeze theorem problem is I want to try and find out what my upper and lower bound functions are. So what is my h of x going to be and what is my g of x going to be? So the way I do that is I first bound the base function that makes up this limit. So the base function, which basically everything is added onto that function, is going to be cosine 2 over x. That's the root, like main part of the function. So I'm going to go ahead and say cosine 2 over x. And what I want to do is bound this between two values. So I'm going to set up my inequality here and try to bound it. So we know that the cosine function can only go between -1 and +1. If you go ahead and look at the graph of cosine, it only goes between negative and +1. The same thing is true for the graph of sine of x. Sine of x and cosine of x only vary between -1 and 1. So what I can say is, on the lower end, I'm going to have 1, and on the positive end, I'm going to have 1. It doesn't matter that I have a 2 over x in here, because cosine of anything, you can put any function in here. It's always going to be between -1 and 1. So now what I'm going to do is I want to transform this middle function to look like what I'm taking the limit of. So what I need to do is I need to multiply all of these things by x cubed because I need to have that x cubed in my limit. So I'm going to have negative x cubed is less than or equal to x cubed cosine 2 over x, which is less than or equal to x cubed. And now we found out what two functions are going to be our upper and lower bound. Negative x cubed is going to be our lower bound, and x cubed is going to be our upper bound. So the second part of the squeeze theorem says that the limit as x approaches a of h of x and g of x needs to equal the same, and they need to be equal to some number L. So if we go over to this example, we want to, in this case, we're looking at the limit as x goes to 0. So we're going to try to find the limit as x goes to 0 of negative x cubed and the limit as x goes to 0 of positive x cubed, which are our upper and lower bounds. So calculating this, we can see that both of these are equal to 0 by direct substitution. So in this case, our L is going to be equal to 0. So now that we've shown that our function x cubed cosine 2 over x is bounded between these two functions, so that's the first part of the squeeze theorem done, and the limit as x goes to 0, which is our a, of these two bounded functions, or these two bounds that are functions, is equal to 0, which is going to be our L value. So therefore, we've shown that this limit, the limit as x goes to 0 of x cubed cosine 2 over x is equal to 0. All right, let's move to our next example. So again, what we want to do is we want to find out what our base function is and bound it. So in this case, our base function is going to be cosine 1 over x. I'm going to have cosine 1 over x. And cosine 1 over x is always between negative 1 and 1, like I said before. So it doesn't matter that I have a 1 over x here, and then the previous example I had a 2 over x. It doesn't matter, because cosine is always bounded between negative 1 and 1. The only exception to that is if you have a coefficient out here. In this case, cosine would be from negative 3 to positive 3. But what we have is just cosine 1 over x. So the trig functions, sine and cosine, not tangent, but sine and cosine, it doesn't matter what input value you give it, it's always going to be between negative 1 and 1. So I'm going to go ahead and bound this between negative 1 and 1. And then I'm going to try to multiply out or add on whatever I need to do to make this middle function look like this function. So what I need to do is I need to multiply everything by x. So what I'm going to have is negative x is between x cosine 1 over x, which is between positive x. And then I want to take my limits. So I'm going to take the limit as x goes to 0, because we're only concerned about x goes to 0 in this problem. X goes to 0 of negative x, and I'm going to take the limit as x goes to 0 of positive x. And what I'm going to end up with is 0 and 0, because direct substitution shows that this is true. So again, 0 is going to be equal to my L value. So now I've shown that this limit is also equal to 0. Let's go ahead and do our last example. So our last example is find the limit as x goes to 0 of x squared sine 1 over x. So again, I want to bound my base function. So my base function is going to be sine 1 over x. And we know that this is going to be between negative 1 and 1. Now, all I need to do is multiply out my x squared to make it transform into this limit. So I'm going to have negative x squared is less than or equal to x squared sine 1 over x, which is less than or equal to x squared. And then I'm going to take the limits of my bound functions. So I'm going to have the limit as x goes to 0 of negative x squared, and the limit as x goes to 0 of positive x squared, which are both equal to 0, which means that the limit as x goes to 0 of x squared sine 1 over x is also equal to 0. So that's how to use and apply the squeeze theorem to three types of problems.